Okay, good morning. I thought let's step back and see where we are now and where we are, where we're going. So we started sort of by assembling some tools, which were homology, unbounded operators in Hilbert space, Hilbert complexes, where I had the Hodge decomposition and Poincare inequality were key things. And then we sort of set up an abstract framework, overlaps with those things. That's here. So in the context of Hilbert complexes, we talked about the Hodge Laplacian and its mixed formulation and that it was well posed and so forth. And then we said, what would you need to do to approximate it with Galerkin methods? And a big takeaway message was the Galerkin subspaces should form subcomplexes of the Hilbert complex, and there should exist bounded cochain projections. Okay, that was sort of, and then we got as many implications of that as we could. Convergence of the method, improved error estimates, convergence for eigenvalues, and so forth. Then we started to make it more concrete. So now we begin in with the concrete case of the de Rham complex. And of course, I've been foreshadowing that all along, talking about the de Rham complex. Actually, I've been calling two things the de Rham complex, to make sure there's no confusion on this. Sometimes I say the de Rham complex is H1 goes to H curl goes to H div goes to L2, say in 3D. And in general, what I'm saying is the L2 de Rham complex is H lambda 0 goes by D to H lambda 1 goes by H lambda n on an n-dimensional manifold. This is the real thing, the L2 de Rham complex. But on a domain in Rn, H lambda 0 is isomorphic via vector proxies to H1, and 1 forms are isomorphic to vector fields in H curl, and n-1 forms are isomorphic to vector fields in H div, and n forms are just isomorphic to L2 scalar fields. This depends on a choice of basis, this isomorphism. This is the more natural object. This is the one that makes sense on any manifold. But we can compute in this form actually only in 3 or 2D or 1D, because in here we don't have obvious correspondences with operators from calculus. But in 3D, there's nothing between 1 and n-1, so we're okay. And by the way, if you think about it for 2D, in 2D, where it's a little confusing because 1 forms could either be things in H curl, or since 2 minus 1 is 1, they could be things in H div. You can make one or the other of those choices, but not both at the same time. So actually in 2D, we have 2 possibilities. We could have the H1 goes to H curl goes to L2, and this would be, or it's in sort of what I usually call H rote, the scalar curl. This would be grad and rote. Or you could rotate the vector fields by 90 degrees, and this becomes then the curl operator, the vector curl operator, into H div, and then this becomes the divergence. These are, of course, isomorphic to each other by taking the perp. Okay. So this is sort of the more general object, and there's a lot of advantages to using this because you see the structure. For instance, you see all these operators are really the same. They're all just made out of one definition of D. And as I say, there are plenty of papers in the literature that have section 1 on H1 and section 2 on H div, curl, and section 3 on H div, and they end up repeating themselves quite a bit in arguments. If you do it this way, you do it all at once. Okay, so then we define the exterior calculus and define the L2 de Rham complex. And now what I want to do today is actually come up with useful, implementable, constructible finite element subspaces of these de Rham complex. So I'd like to come up with spaces lambda 0h, lambda 1h, through lambda nh. Finite dimensional spaces that we can construct in the usual finite element way, so they become a de Rham subcomplex. Let me give you an example to bear in mind. The most famous and probably the most perfect example of this correspondence is for lambda 0h. So you take a triangulation of your domain in n dimensions, etc. And for lambda 0h, you take continuous piecewise linear functions. So in our diagrams, they're determined by giving the value at each vertex. And then there's a unique linear over the triangle that interpolates that. And for lambda 1h, you give the Raviart-Thoma elements, the lowest order Raviart-Thoma elements. This is a space that, well, I'll be calling this space P1 minus lambda 1, for reasons you'll see. And that space has 1 degree of freedom per edge. If you use the HDiv view of things, you would have this diagram. You would give the normal component on each edge. I'll prefer to use the HRot view of things, so we rotate it 90 degrees. And so you give the tangential component on each edge. Then lambda 2h in 2 dimensions would be just the piecewise constants, which have 1 degree of freedom inside each triangle. And if in 3D it would be a similar thing, we would have the piecewise linears, which are given by 1 degree of freedom on each vertex. Nedelec's generalization of the Raviart-Thoma elements, this would be called the edge elements of the first kind. That would be for lambda 1h. Then Nedelec's generalization of the Raviart-Thoma elements to HDiv, which would be the Nedelec face elements of the first kind, 1 degree of freedom per face. And piecewise constants for the 3 forms. Wonderful geometry in these. 1 thing per vertex, 1 thing per edge, 1 thing per face, 1 thing per tetrahedron. And when we assemble these together, so over a triangulation we have spaces of piecewise polynomials, these form a de Rham subcomplex with bounded cochain projections. Then maybe connect a little bit to Anil's talk yesterday. You could take a very combinatorial view and sort of forget you had finite element spaces and say, well, we just have numbers on the vertices, numbers on the edges. That's the cochain point of view. Instead of differential forms, they're cochains. And if you use these finite elements, they're completely equivalent. The cochains don't generalize to higher degree elements, while these ones do. And then somebody asked me about these bounded cochain projections. That's probably a good idea to mention something here, and we'll say more about it. So let's take these spaces. So I have these spaces down here. So we have a projection operator that'll take a differential 0 form, a function, and make it a piecewise linear. We just take the values at the vertices, so we interpolate it into a piecewise linear. So we have the interpolation operator, piecewise linear interpolation. Call it pi 0h. Actually, I follow my notation from later. That will be capital pi 0h. And I'll try to make capital pi's look different than lowercase pi's. And then what about this one? Well, it's the same story. We take our form, our differential 1 form, we integrate it over an edge. A 1 form can be integrated on an edge, and the average value on the edge is the value that we assign here. So we get an interpolation operator that's based on edge traces here, and so forth. Actually, the last one means we take our function and we integrate it over the tetrahedron, so we get the L2 projection into constants. Now, it's an easy exercise that d of pi k is equal to pi k plus 1 of d. They commute. And that's just because these integrals and Stokes' theorem. It's Stokes' theorem. So these are commuting, so they're cochain maps, and they're projections. If you start out as a piecewise linear and you interpolate it, you get the same piecewise linear back, but they're not bounded. That is, they're actually unbounded, densely defined operators on this space here. That is, you cannot take just anything in H1 and interpolate at the vertices, because H1 functions in more than one dimension don't have point values. Only if it's continuous, you could do it. So its domain would be something like, well, you could define the domain in different ways, but you could define it to be continuous. So it would be the continuous functions inside here. That would be a good domain, and the continuous functions inside here, and so forth. Then these operators are well defined, but they're not bounded with respect to the H lambda norm. That means they are not the thing that we need to verify the conditions of our theorem, which says that there should exist bounded cochain projections. Okay, and then it was discovered in roughly the late 90s through contributions of a few people, of whom Christensen and Schroberl are key people, that you could modify these guys by first doing a little bit of smoothing, then applying them, then making some corrections. And the resulting guys still were commuting and projections, but now we're bounded. And I'll go over that thing. It's a sort of technical point, but you use a smoothing argument, and then you can get different projections. They're not implementable or anything, but they exist, and therefore the theory applies that these elements have bounded cochain projections. Okay, that's sort of where we are and where we're going. Any questions? Okay, and then I just wanted to make one comment on exterior calculus. So the lecture I've been least sure about was the exterior calculus lecture, so I appreciate feedback. I was a little afraid that if you knew it, you were just hearing something you knew, and if you didn't know it, it was going by too fast to learn anything. I'm not sure. But let me just take a more sort of engineering textbook point of view. In the end, the takeaway message is really, well, in a one form is something of the form A1 dx1 plus A2 dx2 plus A3 dx3 in 3 dimensions. And calculating with differential forms is really easy. So the A's are functions. So if you want to, let's write down a specific one. X squared y, or maybe I'll use the ones and twos. X squared, x1 squared x2 dx1 plus x1 squared x3 dx2 plus dx3. Okay? That's a one form. So what do you do with one forms? Well, you differentiate them. So let's call this u. So du, what is it? Well, you take the partial derivative of this with respect to x1, you get 2x1 x2, and then you put an extra dx1 in there. So you du dx1, du is du dx1, dx1 plus du dx2, dx2, etc. So you put this here, and then we had a dx here, so that's wedged with dx1, but then we cancel that out because 2 dx1s gives us 0. But now we have to differentiate this with respect to x2, so we'd get plus x1 squared, and the derivative with respect to x2 goes away, and I get a dx2 wedged dx1. And then I have to differentiate this with respect to x3, but that's 0. So then I go to this one, and I get something similar. This time I get plus 2x1 x3 dx1 dx2, and plus x1 squared dx3 dx2. And this one, I get 0. So that's it, except it's not quite in this form because I like to have these things increasing. So then I use that dx2 dx1 is minus dx1 dx2. So I put a minus sign here and make this dx1 dx2. And then I see I can combine these two terms. So it's 2x1 x3 minus this, that's this term. So that's it. So it's very simple to do it. If you just use this rule, which they taught you in first year calculus, but they didn't tell you what it means, it works out. Even more true for the integration. What's the integral of this one form over a curve or a line segment, f? Well, you learned in your third semester of calculus, you learned to make sense of expressions like this and how to calculate them, and it'll work. This definition gives it a meaning. It's the same answer. What about the wedge product? Well, what if I wanted to wedge u with v, which is cosine x1 dx2? So I just wedge it with each of the three pieces, and I'd have a dx1 wedge dx2. dx2 wedge dx2 would go away, and dx3 dx2 is minus dx2 dx3. So any help if I do it in more detail? Let me do the pullback. The pullback is an interesting one. So we have a domain omega hat and a map to a domain omega. We do this in finite elements all the time as for zero forms. This map phi takes x hat to x. We have a differential form here, u of x hat. U of x. We'd like to define the corresponding function here, u hat of x hat. And the rule we always use, write down in finite elements all the time, so this u hat is going to be phi star of u. And the rule we always write down is u hat of x hat equals u of x, which is another way of saying that u hat equals u composed with phi. That's the pullback for zero forms. What would we have if we had here a two form? Let's say we have f of x1, x2, x3, so f of x, dx1 wedge dx2, for example. So that's u. What would be the pullback? Well, it would be simply for x, you put in phi of x hat. So it would be f of phi of x hat. If you want to think of it, that's f hat of x hat, or f composed with phi of x hat. Then for this x1, well, what do you use? You use dx1, and I want to write it in terms of dxj hats. So I use dx1 is the partial of x1 with respect to x hat 1, dx hat 1, plus the partial of x1 with respect to dx hat 2, dx hat 2, plus the partial of x1 with respect to dx hat 3, dx hat 3. And I do that for each of the guys, not only the first, but also dx2 and so forth. And when I say x1, derivative of x1 with respect to x hat 1, of course, I'm talking about the derivative of the first component of phi. That's all. And so I would stick that in for dx1, and I would stick in the similar expression for dx2. So I get my f, so over here, I would get this as this f of phi of hat would be d phi 1 dx hat 1 dx hat 1 wedge d phi plus d phi 1 dx hat 2. Let's do it in 2D, dx hat 2. And then I'd have to wedge that with the same thing for the second component, d phi 2 dx hat 1 dx hat 1 plus d phi 2 dx hat 2 dx hat 2. And then I would expand that out, so I would get things like f composed with phi of x hat times d phi 1 dx hat 1. And I can pull this out, this zero form out, d phi 2 dx hat 1 times d. Well, that would give me a dx hat 1. dx hat 1, that would go away. But this term times this term would give me a dx hat 1, dx hat 2. So that term would be d phi 2 dx hat 2. And I'd get dx hat 1, dx hat 2. And so forth. So you just plug in this formula, which is the natural formula, and use the fact that the wedge product is skew symmetric, and you can write it out. And this defines all the pullbacks. So that's where the Piola transform comes from and so forth. Okay, I think I'll, any questions on the differential forms? The Hodge star. Yeah, yes. So let's go into 4 dimensions and look at a 1 form. A1 dx1 plus A2 dx2 plus A3 dx3 plus A4 dx4. That's a typical 1 form. Or a 2 form would be some, well, so let's pick one term because it's linear. So let's focus on some A dx3. And I want to take the hard star of it. And then after I do that one, I'll do a 2 form. So I'll look at some B dx2 wedge dx4. And I'll ask what the hard star of that is. Okay, all you do, the A doesn't enter into the story. It just sits there. Hard star is an algebraic operation, so you can pull out a function. And so we need to, so it's A star dx3. And star dx3 is just the other dx's, dx1, dx2, dx4. You leave out 3 and put all the other ones in a row here. That's the definition of star dx3 plus or minus. And that's the answer. And how do you know whether it's plus or minus? Well, you write down this sequence 3, 1, 2, 4, and you decide whether this is a positive permutation or a negative permutation of 1, 2, 3. So what would this one be? It would be B dx1 dx3 with a sign. That's it. So it just takes the components and puts them in other spots. Okay? And so a 1 form is a vector field in 3D. A 2 form is a vector field, so it just takes the components of some vector and makes some other vector. In that case, it's the identity.
Are those supposed to be right products?
So, right, as one gets better at this, then you make your wedges smaller and smaller till you barely write them down. And of course, in calculus, that's where you started, right? In calculus, you write the integral of f dx1, dx2, dx3. And here there's actually a difference from the calculus notation, because I suppose if we switch the order here, we probably wouldn't change the sign, because they're not really thinking about an oriented space. They agree on the right-hand rule from day 1, and everything's a right-hand rule. Yeah?
This is all flat space, or can we make it curved?
So what have I done that uses flat curves, and what have I done that uses flat space? So first, let's talk about the operations. Exterior differentiation, exterior integration, wedge product are on any manifold. Hodge star is not. Hodge star requires a metric to decide which is the volume form and what the inner product is. It's defined through an inner product. dx1, dx2, dx4, well, I use the fact that I have this dxi is the dual of vector to ei, dxi ej equals delta ij. It is and also we have a coordinate function xi from a flat space in Rn to R, which is just the ith coordinate, and the exterior derivative of this is that, so the notation's okay. So in that sense, requires a flat space. But for many operations, like computing the exterior derivative, I could have used, instead of the coordinate functions x1 through xn, I could have used any coordinatization. And this would tell me how, so for example, this way to pull back from a curved manifold, if I have some coordinate functions on this manifold that relates it to flat space, which maybe I call x1 through xn, but they're not the ith component. And then I get a coordinatization of this by composing with phi. That follows these formulas. So some of it yes, some of it no.
So if we want to use the framework for hemisphere, for flow of something like hemisphere, we can do it.
So the abstract framework should work generally for Riemannian manifolds. We definitely need the metric to be talking about the Hodge star and so forth. And yes, so that's basically true. I would say the applications haven't been fully worked out. I think it's a good area to work in is when you have good applications where you need to do mixed finite elements on surfaces. This is probably the place you should be working. Any other questions? Okay, so let's get started with finite element differential forms. There's going to be one more thing that fits in the tool category, and that'll come today, and that's going to be the Koszul complex. Okay, so our goal is to define the finite element spaces lambda kh and h lambda k. And they should satisfy, of course, approximation properties. They should form subcomplexes with bounded cochain projections. So how do you make a finite element space of anything? What are finite element spaces? So go back to the definition that was highlighted by C.R. Ley in '78 in his book. So a finite element space consists of, you triangulate your domain, typically through simplices, but also maybe cubes or distorted cubes, quadrilaterals, possibly things more complicated. But we'll, for the time being, be talking about simplicial triangulations. And then on each of your elements, those are the elements, for each of your elements you say what the functions are going to be. Like I've been doing, piecewise linears, they'll be linears. Or piecewise constants, they'll be constants on the highest degree dimension simplices. But then you have to say how you paste them together, and those are these degrees of freedom. So formally, degrees of freedom are functionals from the space of shape functions to the real numbers. On an edge, that functional might be the integral of the tangential component over the edge. And the degrees of freedom have to be unisolvent, so they form a basis. You take all the degrees of freedom you had, they're a basis for the dual space of Vt. And then there's one more aspect of the definition that I wish C.R. Ley had written in his book, because people have sort of forgotten it. He certainly had it in his mind, that every degree of freedom is either associated with a vertex, or associated with an edge, or associated with a face, or associated with a whole tetrahedron. And if two tetrahedrons, say, share a face, the degrees of freedom of one of them are in correspondence with the degrees of freedom of the other one, so that the following definition makes sense. The finite element space assembled together over the whole domain, that's VH, that's defined as functions that when you restrict them to one element, belong to that shape function space. And if two elements share a common face, or a common edge, or a common vertex, the degrees of freedom are the same from both sides. So it's VH is the set of V in, say, L2 of your whole domain, such that V restricted to T is in VT for all T in your triangulation. And the degrees of freedom are single valued on all faces. So if we have two triangles and we give the tangential derivative in those three edges, and then we do it for the next guy, these two numbers we give the same number. So let's do the simplest example that most people will have seen before, but let's just go through it in this language. So Lagrange finite elements, or in our new language, elements for zero forms. So the triangulation is a bunch of simplices that fit together in a simplicial complex. The shape functions are polynomials of degree at most r on t. So PR of t means you take polynomial functions on Rn, of degree r or less, and you restrict them to t. And now the degrees of freedom have this one simple formula, which is you associate degrees of freedom with the vertices and the edges and the faces and so forth. With a face of any dimension, d, you associate the integrals over the face of the restriction of the zero form to the face, weighted by a basis of functions in polynomials of degree r minus d minus 1. So we'll have to stare at that a little bit. So first of all, there's already a slight abuse of notation. I said degrees of freedom were a finite set, and now I have them parameterized by an infinite space, a finite dimensional space of polynomials. I mean, take any basis you want for these polynomials, it doesn't matter which ones, and those will give us degrees of freedom. So let's take the case of an edge first, a dimension 1 edge. So what are the degrees of freedom associated with that edge? Well, according to the formula, it's the integral over the edge of the restriction of u on the edge, weighted against a polynomial, and the polynomials are polynomials of degree r minus 2, r minus d minus 1. So, for example, if we took the case of polynomial, let's say r is equal to 3, so we're talking about cubic Lagrange elements, then r minus 2 is equal to 1, so we would put polynomials of degree 1, that's a two-dimensional space on the edge, so we'd integrate it, and we'd integrate it versus s. So we're really talking about two quantities, the integral of u on the edge, and the integral of u s ds on the edge. Those are the two degrees of freedom on that edge. On the interior of the face, we'd have the integral against only against constants, so only one-dimensional space, pr minus 3, so there'd be 1 degree of freedom on the face. What about on the vertices? I skipped that one. So we should integrate on the vertices, the restriction to the vertices, against polynomials in degree p r minus 1, if it's 3 p2. Well, what does it mean to be a polynomial of degree 2 on a vertex? Well, on a vertex, there's only one function, the constant. It's a polynomial of degree 0, so it's in here, but there's nothing more. It doesn't matter what degree I write. So there's only one thing here, and of course, it's just the integral of u times 1, which just means u of v. So what do we get? We get the values at the vertices, the integral of the moments up to degree r minus 2 along the edges, the integral of the moments on the faces of degree r minus 3, and if r is big enough that we haven't gone negative yet, the integral in the interior of moments of degree r minus 4. This is the picture for r equals 3 here. And what do we have to do to complete the definition of a Lagrange finite element? Well, we have to prove that the number of things here, we have to count them, and we have to say that's the same as the dimension of P3 of t. So let me do the count in my mind. So what do we have here? We have 1 point here, and then another 3, and then another 6, so we're up to 12, and then another 10, 22, and then another 15. That doesn't sound right. P3, so let's count P3. So what's the dimension of P3 in 3 dimensions? Well, the general form is r plus n choose n. So this would be 3 plus 3 choose 3, which is 6 factorial over 3 factorial, 3 factorial, which is 6 times 5 times 4 over 6 is 20. Oh, except that that's picture, I see, that's because that picture is not P3, that picture is P4, which is why I have 3 things on each edge. This picture is P4, I have 3 things on each edge, I have 1 thing on each vertex, I have 3 things in each face, and then I would have constants, so 1 thing on the inside. So let's do that P4 case. So this would be 4 plus 3 choose 3, which would be 7 times 6 times 5 times 4 divided by 6, which, wow, that can't be right. Is that right? Why am I having so much trouble counting? P4 is 4 plus 3, choose 3. So 7 times 6 times 5 times 4, then I divide by, so I have to divide this 3 factorial divided by 3 factorial, right? What am I doing wrong? Maybe I'm not. Is it that big? Can't be that big. Oh, that's right. I had to divide by 4 factorial. So, sorry. 7 factorial divided by 3 factorial, 4 factorial. So that's 7 times 6 times 5 divided by 6, which is 35, which is the right answer. Okay, and then let's count the number of degrees of freedom another way. There are 4 vertices and 1 degree of freedom, so 4 times 1. Then there are 6 edges, and each edge has 3 degrees of freedom. It's r minus 2, polynomials of degree r minus 2 in 1 dimension. That's r minus 1, so that's 3. So we have 6 times 3. Then we have 4 faces. And now we need polynomials on a 2-dimensional face of dimension 1. So that's linears in 2 dimensions is 3 again. And then in the interior, we have only 1 interior. And we have piecewise constants there in 3 dimensions is 1. So we get 4 plus 18 plus 12 plus 1, which is 35. Yeah? Yes, that's another basis. This is not the Bernstein basis. That's a good point. Maybe I'll say a little something about the Bernstein basis. The control points are the same as Bernstein basis, but, I haven't given you a basis, but this gives you a natural basis, which is, you said, one of them to 1 and the others to 0. And with Bernstein, you would get something that has sort of that shape. But this wouldn't. This would be 1 at exactly that point and 0 at the others. It wouldn't be monotone, right? So this is the Lagrange basis, the picture that'll make it clear to you. Let's do P3 in 1 dimension. The functions we'll get here are the cubic that's equal to 1 here and 0 at these points, which would be this guy. And then the next one, of course, would be that guy and so forth. And of course, you're thinking of ones that would look like this and this, quite different. I may, especially if you're interested, I might talk about what's the Bernstein basis for differential forms at on the last day. So let's actually formally prove this theorem, because it'll give us a hint of how we do it for differential forms. So the shape functions, I just repeated from the previous slide, the shape functions are polynomials of degree r or less. And the degrees of freedom are these integrals weighted against polynomials of degree r minus d minus 1, where d is the face dimension. So for the count I did over here, in general, is the following. You sum over all dimensions of possible faces from 0 to n. And how many faces are there? Well, to get an d-dimensional face of an n-dimensional simplex, you have to choose d plus 1 vertices out of the n plus 1 vertices. So it's n plus 1, choose d plus 1. And the dimension of polynomials of degree r minus d minus 1 on a d-dimensional space is you add the degree and the dimension, so r minus 1, and you choose the dimension, and you get that binomial coefficient. So then you use a binomial identity. There's an identity when you have the denominators both an increasing sequence, and the way you get that identity is you take 1 plus x to the n plus 1 and 1 plus x to the r minus 1, and you expand this out in a binomial series and this in a binomial series, and then you also expand 1 plus x to the n plus r in a binomial series. And you equate terms, and you see that this thing is the same as this thing. So that's how you compute the, so in that way, and then this thing you recognize is just the dimension of PR in n dimensions. So the number of degrees of freedom works out to be the dimension of PR by that little combinatorial argument. Okay, now we want to prove unisolvents. So here's an example of where it really helps to go to a general framework. The best proof of unisolvents is induction on the dimension n. If you have a viewpoint when you write your papers that n is always 2 or 3, you don't tend to do induction on n, which means you end up giving 2 different arguments, while here you give 1 and it works for all n. So how do we do induction on the dimension? Well, when we look at this Lagrange element, let me take the P3, say, so I don't have to draw so many dots, and so forth. Well, suppose I look at just one face. So that one face has dots at each vertex and 2 on each edge, and 1 in the interior. So this is P3 of our tetrahedron, and this is P3 of our face. And this guy, the degrees of freedom are exactly the degrees of freedom for the Lagrange elements of degree 3 in 2 dimensions, because there's the formula is the formula, and the formula has R and D in it, but it doesn't have N in it. Okay, and also a function, if U is in P3, then the trace of U on the face is in P3 on the face. So now, suppose we have a U in P3 of the tet, and all these degrees of freedom vanish. Then the trace of U is in P3 of the face, and all its degrees of freedom vanish. So by deduction, the trace on the face of U is equal to 0. Okay, that's the inductive step. And that happens on every face. So therefore, U is not only in PR of T, but it's in the PR of T's that are 0 on the boundary. Trace on boundary of U is equal to 0. So now we're reduced to an easier question. If U is in polynomials of degree R in T and it vanishes on the boundary, and the degrees of freedom of U on the whole tet, we already took care of the boundary ones, so the only ones we care about are the last ones, which are U weighted against polynomials of degree R minus, it's R minus n minus 1, right, going back to, well, it's the formula at the top, and you take D is equal to N. So if this is true, we have to prove that U is identically 0. So we have a polynomial of degree R, it vanishes on the boundary of a simplex, and it's orthogonal to PR minus N minus 1, so it vanishes. Okay, well, a simplex, so all you do is you define the function, let's number the vertices 0, 1, 2, 3. And on the face opposite 0 will be defined by the equation lambda 0 is equal to 0, normalized by, say, lambda 0 is equal to 1 at this vertex. So that's a linear function, the barycentric coordinate function. That's the linear function that defines this face, the plane containing that face. Okay, now U is 0 on that face, so it has to be divisible by that linear function. So to say trace U equals 0 on face 0, that's the same as to say that lambda 0 divides U. And trace U is equal to 0 on the whole boundary, on all the faces. That means that lambda 0, lambda 1 through lambda n divides U. So U is equal to lambda 0 through lambda n times some P of x, and U is a polynomial of degree R, and this is a polynomial of degree n plus 1, so P is a polynomial of degree R minus n minus 1. Okay, and now the integral of U times that exact polynomial P, that's the integral of lambda 0, lambda 1 through lambda n times P squared. And the lambda functions, they are 0 over here, 1 over here, and between 0 and 1 in between. These are positive on the entire triangle, and p squared is certainly positive. So this is, if we have this is equal to 0, we have a problem. The problem is p squared couldn't be positive, it has to be identically 0. Right? If p were not identically 0, then this would be positive and it couldn't be equal to 0. So that's the usual argument. Okay, is that clear? So we're going to carry that argument over to finite element differential forms. Yeah.
You say you have to choose such DOF. You have a very nice property.
If I choose such DOFs.
Solvency and belongs to H1.
The belongs to H1 I haven't said, but that's a good point.
The other direction also true. So the DOF should be chosen in such a way that, I mean, if your finite element space belongs to H1, the DOF must be what you have.
No, that's not, the second statement is not true, but this is a good point you're bringing up. So where are we now? Let's go back to the Lagrange example. So now we have the space that I would call PR of a triangulation. That's our VH. And by definition, this is the set of all V in L2 of omega, such that V restricted to T is a polynomial degree R on T. And V is continuous at the vertices. And the integral, it's a little hard to write if you take if F is a common edge of T1 and T2 of two triangles, and you take V restricted to T1 and take the integral of that versus a Q of S ds on F, and you do the same thing with T2, you get the same answer, where Q is in PR minus 2 of the edge, and so forth. So the degrees of freedom are single valued. That's the definition of our space. So the first point Young-Ju made is that V of H is contained in H1 of omega. That's not the definition, it's a theorem. How do you prove that theorem? Well, actually, we did the work for that theorem in proving unisolvents, because the restriction of U to some face of the thing is Lagrange 1 degree lower, and the unisolvents then says the restriction of U to a face is uniquely determined by the degrees of freedom. So we have, if F is a face of any dimension in the triangulation, then U restricted to F is single valued. Has the same value no matter which tetrahedron you think it's a member of, because we have unisolvents from those degrees of freedom. Okay, another way to say that is that U is continuous. No matter how you get to a point, you get the same value. So we know that these functions are continuous piecewise linears, and of course continuous piecewise polynomials, or continuous piecewise smooth functions belong to H1. So that's a proof that VH contains an H1. Actually, something stronger is true. VH is not only contained in the set of V in H1, such that V restricted to T is in PR of T for all T. That's what I just indicated we've proven, but actually this is an equality. Any continuous piecewise polynomial will be in this space. Why is that true? Because, well, a continuous piecewise polynomial has a value at the vertex, has an integral over the edges, and so forth. And we just take those values. There's a unique guy in this space with those values. And since we have unisolvents, it must be that guy. So the way you check whether you have actually equality here is you just make sure that, I'm sorry, that was not a good argument. I should say this is the same as the set of V in C, such that V restricted to T is in PRT for all t. Because a piecewise smooth function is in H1 if and only if it's continuous. And every continuous function has these degrees of freedom well defined, point values and integrals. And therefore, everything in here is one of these. An example where that would not be true would be, for example, here's another space. Take T as a tetrahedron. The shape functions are going to be P3 yet again. Let's do it in 2D. T is a triangle. The shape functions are P3 yet again, but our degrees of freedom are going to be the values at the vertices and the values of du dx and du dy at the vertices. So 3 degrees of freedom associated to each vertex. And then, well, P3 is dimension 10 in 2 dimensions, and there's 3, 6, 9, so I'll also put 1 in the interior, the integral over the triangle in the interior. This is unisolvent, so it's not hard to prove that if all these 10 quantities vanish on a cubic, it vanishes. Because this is a Hermite cubic, it vanishes on the faces, blah, blah, blah. Okay? And because this is a Hermite cubic, it'll vanish on, if it's completely determined on the edge by its value and its tangential derivatives on the edge, it'll belong to this space. But this one won't equal that space. It's a different space. And the reason it's a different space is because there are, all these guys are C1 at the vertices, and there are plenty of continuous piecewise cubics which are not C1 at the vertices. Then another point that maybe it's worth bringing out here, I took it to degrees of freedom, let's say for our cubics, let's go to quadratics in 2D. I take as our degrees of freedom the values at the vertices and the integral over the edge, on the edges. Many other people take the values at the vertices and the value at the midpoint of the edge. These are completely equivalent in the sense you get the exact same space. Because if you know all these values, that completely determines. So, well, for a quadratic that, how should I say it? If all these quantities are continuous, then, let's see, how should I say it? What's the easiest way to see that these things are completely equivalent? Well, one way to see it, but there might be an easier way than this, is that if we assemble the space and ask what space we get, by the same argument I gave before, we get this. It's certainly contained in here, because these 3 quantities determine a quadratic on the edge. And anything in here, all those quantities are meaningful, so there you get something in there. So you get the same space from this as if with point values or integrals. What really matters is the span of the degrees of freedom associated with a face. The space spanned by those degrees of freedom, not the particular choice of degrees of freedom. Okay, any other questions? Okay, so now let's move to differential forms and see how we can carry this stuff over. So first we'll start with the analogous space of k-forms instead of 0 forms. So these are k-forms whose coefficients are polynomials of degree r or less. So everything in the form of a sigma dx sigma 1 through dx sigma k, where the a's are polynomials. That's all. So again, if you think of 1 forms, these are vectors. There's a vector worth of coefficients, and each is a polynomial of degree r. We'll also need the homogeneous polynomials of degree r. And so when I write hr, I mean homogeneous polynomials. Every monomial is of exactly degree r. And those could also be taken as coefficients for k-forms. Let's compute the dimensions. Well, that's easy. It's the number of these dx sigma I, 1 through sigma k. So that's n choose k. And each of them has a coefficient in an r plus n choose r dimensional space. So it's the product of those 2 binomial coefficients. And here's another identity. This is a really easy identity. Write down the definition of the binomial coefficients and do the algebra. These 2 things are the same. If we do the same thing for homogeneous polynomials of degree r, the dimension of homogeneous polynomials of degree r in n dimensions is the same as all polynomials of degree r in n minus 1 dimensions. So it's r plus n minus 1 choose r. And those are the coefficients of n choose k different dx alternators, dx sigma 1 through dx sigma k. So we get this. And that can also be simplified, and the reason I like this form is you can see the ratio of the two of them. The homogeneous polynomials account for n over n plus r proportion of all the polynomials of degree r. So for example, for degree 0, they're the same. Okay, now polynomials form a de Rham subcomplex on the domain you're looking at. So this could be on the whole of Rn, or say on one tetrahedron, is where we're going to use it. And if you take a polynomial function of degree r, and you take its exterior derivative, well, of course, you get a polynomial function of degree r minus 1. You take its derivative, you get r minus 2, because each time you do one partial derivative. So the degrees go down when you differentiate polynomials, at the same time as the form degree, of course, is going up, because we're doing exterior differentiation. And so we get this polynomial de Rham complex. And differentiation takes degree r things to exactly degree r minus 1. So it keeps homogeneous stuff homogeneous. So if you have a homogeneous degree r, the derivative is homogeneous degree r minus 1, 1 form, and so forth. Okay, so now an interesting question is the following. Okay, so you take a tetrahedron, and you have that complex. Polynomial of degree 5, 0 forms, and then polynomial of degree 4, 1 forms, and polynomial of degree 3, 2 forms, and polynomial of degree 1, 3 forms. What's the cohomology of that sequence? It's not going to have anything to do with the topology of anything, because polynomials are polynomials. You get the same space of polynomials whether the domain has 11 holes or whether it's all of Rn. So what's the question we're asking? We're asking, well, if you have a vector polynomial of degree r minus 1 and its curl is 0, can you write it as the gradient of a polynomial of degree r? Or if you have a vector field of polynomial degree r and its divergence is 0, is it the curl of a polynomial degree r plus 1? And if not, by how much does it miss? Well, some of those are easy to answer. Start in the first one. If you have the gradient of a polynomial is 0, what is it? Well, it's a constant. So we have homology of the constants here, just like we have for the true de Rham complex. If we go down to the homogeneous level, there's no homology except at the level of constants. The next one's easy too, because if you have a vector field and its curl is 0, well, it's the gradient of something. But if the gradient of something's a polynomial, that something's a polynomial of 1 degree higher. But the next one's not so easy. If you have a polynomial vector field and it's divergence free, it's definitely the curl of something if there's no holes. But is it the curl of a polynomial? So we'll answer that question in a slide or two, and the key tool is going to be the Kazul complex. So this is the last major tool, and it's again a simple one, but sort of abstract and so forth. Actually, Anil was getting at it in some ways in his talk, and I'll point that out. So, yeah. Not with respect to, so this is invariant under the affine structure of Rn. So affine structure. So this is definitely using the fact that omega is a domain in Rn. Polynomials make sense over vector spaces or more generally affine spaces, but polynomials don't make sense on manifolds unless they're coordinate dependent. Right. So at this point we're going affine. And then when we get to the question about manifolds, well, we're going to have to think of manifolds. To do finite elements, we're going to have some piecewise affine structure floating around, or we're going to have to choose coordinates, something. Okay, so the Kazul complex. So this is incredibly important. This didn't enter numerical analysis till our paper in 2006, but I think it's been missing from numerical analysis. We needed it. So let me get back on the right slide. So what I'm going to do is I'm going to give you a map that's going to take a K form and give you a K minus 1 form. And almost every time I apply it, I'm going to apply it on a polynomial K form, but I'll define it for any K form. Called kappa, the Koszul differential. And it's very simple. So what's a K form? That's something that takes a point x and k vectors. So if u is in here, it takes a point x and k vectors, and it gives you a number. So now, what's kappa u? That's supposed to take a point x and k minus 1 number of vectors and give you a number. And you say, well, how am I going to get a number out of that? Well, I better take u at x, because that's the only thing that gives me a number. But now I have k slots I have to fill in. Well, there's an obvious choice for k minus 1 of them. So let's make it the last k minus 1 of them. I'll put in v1 through vk minus 1, and I have a hole to fill in. So I need to put a vector in there. What vectors are on the board? v1 through vk minus 1, but I can't put any of them in here because this is alternating. I get 0. The only other thing around here is x. Now, x is a point, not a vector. But if you're in Rn, a point is a vector. So you just think, oh, that's a vector. I could stick it in here. That's the Koszul differential. So it uses the fact that we can identify points in vector space with vectors. Points in Rn with vectors. Another way, if you want to write it in a little fancier notation, we can think of a vector field, which sometimes you would denote, say, well, you could denote it capital X or little x. What's x at x? X at x is x. Of course, there's another name for that. It's just called the identity. The identity is a vector field on Rn. Here we have Rn, and at every point we have a vector, which is exactly that vector that points from the origin to that point. The identity is a vector field. This is the identity vector field. And this is the contraction. So that's another way to write it. Kappa u is just the contraction of u with the identity vector field. Okay. So that's it. That's the Koszul differential. So if you'd been scared about it, now you don't have to be scared anymore. So here's an easy exercise. Kappa kappa is equal to 0. Well, that comes from the fact that if you contract with the same vector field twice, no matter what that vector field is, what does that mean? This means you take u and you stick in v in the first two places. Well, you stick the same thing in twice, you get 0. So the contraction of a form with a vector field, the same vector field twice, is always 0. So the Koszul makes a complex. Let's calculate some Koszul's. Well, first let's calculate Koszul of a 0 form. So we just have a function f, which is just a function. Well, this is a minus 1 form, so it's 0, because there are no minus 1 forms. So that's an easy calculation. Let's calculate Koszul of a 1 form, say dx1. Well, at any point x, it's a 0 form, so f is a 1 form. F dx1 is a 1 form. So this whole thing is a 0 form. So I put in a point x and nothing else, no vectors, and I get a number. What number do I get? I get the number when I take f of x dx1 and I apply it to the vector x. I apply it to x viewed as a vector. Well, what's dx1 of a vector? dx1 of any vector is the first component of the vector. So this is this is f of x times x1. In fact, a simpler calculation is what's Cazul of dx1? It's just x1. So now it's sort of weird. dx1 is a 1 form. Cazul of it's a 0 form, which is a function, and the function is the first coordinate function. Cazul is sort of erases d. And Cazul doesn't care about the function part, they just pull out. So if I can, Cazul of anything times dx1 is the anything times x1. Well, now what about if you want to go to higher forms? Let me tell you what the answer is and why you get it. You have a Leibniz rule for Cazul, which is Cazul of omega wedge mu, or u wedge v, is the Cazul of u wedge v. This is a k form, and this is a j form. The Cazul of u wedge v plus or minus u wedge the Cazul of v. This is negative 1 to the k. That comes directly from the definition from the alternating nature of differential forms. So you can easily check this thing. So that makes it easy to figure out what Cazul of, say, dx1 wedge dx3 is. Well, it's Cazul of dx1, which is x1, dx3, then minus dx1 wedge the Cazul of dx3, which is x3. And so it's x1 dx3 minus x3 dx1. And in general, if you have Cazul of dx sigma 1 wedge dx sigma 2 wedge dx sigma 3, you just cross out one of the d's, so you get x sigma 1 times the other dxi's, and you do that for each one in turn and take the alternating sum. And if there's an f here, you leave the f here. So it's okay, so it's easy to calculate also. What does it come down to in the concrete case of R3, where we could use vector proxies and think of 1 forms as vector fields and 2 forms as vector fields? Well, it takes, even if you can forget the p's here for a moment, it takes a 3 form, which is a scalar function, and you multiply it times x1, x2, x through x3, x1, x2, x3, that vector, and you get a vector field. That's our 2 form. Then you take that vector field, the Cazul of that gives you another vector field that's crossing it with x1, x2, x3. And the third Cazul operator, which takes a 2 form, which takes a 1 form and gets you down to a 0 form. So the first one is 3 form down to a 2 form, 2 form down to 1 form, 1 form down to a 0 form. This one is dotting a vector with x1, x2, x3 to get a scalar. And we see from this definition that every time you apply Cazul, not only do you get rid of 1d and therefore lower the form degree, but you bring in 1 more x, so you raise the polynomial degree by 1. So that's why Cazuls are usually applied to polynomials, because they take polynomial n forms to polynomial n minus 1 forms of 1 degree higher, and so forth. So you take a polynomial 3 form, it's a scalar function, and you multiply by x, you get a vector function of 1 degree higher. Take a vector function, polynomial function, you cross it with x, you get a vector polynomial function of 1 degree higher, and so forth. And then there's this wonderful formula, and that is the formula for the Cazul operator. That is so useful. So many times that is exactly what you need to go on. And it's useful enough, I'll prove it 2 ways. So one, let's just do the calculation. I don't know, did I write anything down? Here, we'll do the calculation. So I'm trying to prove that if you take a k form, and it's a homogeneous polynomial of degree r, you hit it with d. Actually, let's back up. So you take a k form, homogeneous polynomial of degree r. So the Cazuls also take homogeneous to homogeneous, because you always multiply by x. So if it's a degree r, you take kappa of it, you raise the, I better put this on the board. I take a homogeneous of degree r k form. If I take d of it, I get differentiation lowers polynomial degree, but raises form degree. But if I take kappa, that lowers form degree, but raises polynomial degree, so it gets us back here. On the other hand, I could have gone kappa this way, and that would have raised my polynomial degree even more, but lowered my form degree even more. And then I take d going back, and that would bring me back. So I can talk about d kappa plus kappa d, and that'll take homogeneous polynomial degree rk forms to the same space. And the statement is this is just the identity map times a constant. This is r plus k, the sum of the polynomial degree and the form degree, times the identity. So let's prove that. So this is actually a new proof that I came up while I was writing these lectures. I'm sure it's not new, but it's new to me. I'm going to improve it by induction on the form degree. And let's look at the case k equals 0, because you've probably seen it before. For k equals 0, so now this is a 0 form, this is a 1 form, and this is gone. So we're just trying to show that kappa d of a homogeneous polynomial of degree r function is just r times the identity. Okay, so what does this mean? It says you take a homogeneous polynomial of degree r, you take its gradient, and then you dot it with x. And what you get is r times x back again. That's what's called Euler's identity. A gradient of a homogeneous polynomial dot x is just r times the polynomial. Of course, it's very simple to write down. So that starts us off on an inductive proof of the homotopy formula. So assume we've proven the homotopy formula for k minus 1 forms, and now we want to verify it for k forms. Well, of course, a k form can always be written as some k minus 1 form, wedge an extra dxi, some sum of those. This is a general k form, can be written in this form, where this is a k minus 1 form. So I really only have to prove it for taking a k minus 1 form and wedge with some dxi, and I want to prove the homotopy formula d kappa plus kappa d. Of this, I would like to prove is r plus k times it. That's the inductive step. Okay, so now we just compute the two things. Can't be hard, right? These are simple definitions. D and kappa are both simple guys. So we take omega wedge dx, and I use the Leibniz rule to apply kappa to omega wedge dx. That's kappa omega wedge dxi, plus -1 to, well, omega is a k minus 1 form, -1 to the k minus 1, omega wedge, and then kappa of dxi is just xi, omega wedge xi, which really just scalar product of omega and xi. Okay, then I have to take d of that thing. So I use the Leibniz rule for d. That's d of kappa omega wedge dxi plus -1 to the k minus 1. And then I have to, oh, why didn't I get two terms here? What's that? Because d squared is 0. Thank you very much. So here it's just d on this, and that, but no d on that term. Now I go to this term. I get d on this and d on this because there's no d squareds. So I get d omega wedge xi plus omega wedge dxi. Okay, so that's what you get when you do d kappa. What do you do when you do kappa d? Well, you get d omega wedge dxi, and then again d squared is 0, so there's no other term here. And then you kappa that, so you get kappa d omega wedge dxi, plus now it's -1 to the k, because d omega is a k form. -1 to the k, d omega wedge kappa of dxi, which is xi. Now you add these things together, and the one term you don't like cancels out because it's with a -1 to the k minus 1 here and a -1 to the k here. And what's left is d kappa omega plus kappa d omega wedged with dxi, and then also omega wedge dxi. The inductive hypothesis tells us this is r plus k minus 1 times omega. So we get r plus k minus 1 omega wedge dxi plus another omega wedge dxi. So it's r plus k omega wedge dxi. And I will stop here with one more observation because of Neil's talk yesterday. He pointed out Cartan's magic formula. And that's another way to prove the homotopy formula. So, second proof by Cartan's magic formula. Cartan's magic formula is that if you have a vector field V, you take the Lie derivative of V of the contraction. I hope I get so I want to have d omega contract of a vector of a form omega. This is the same as d omega contracted with V plus omega d, that's kappa d, and now I need d kappa, so, and plus d of omega contracted with V. That's Cartan's magic formula. This is V is a vector field, and omega is a K form, and that's it. Okay, and the Lie derivative, what was the Lie derivative? Well, you take your domain, you draw your vector field, you define a map phi, so, parameterized by a time variable t, which takes a point x and flows it along a time t to a point phi t of x. So that just means that d dt of phi t of x is equal to your vector field evaluated at phi t of x. And phi 0 of x is x. And now we're going to apply this formula with V as being the identity vector field. So V of phi of t is phi of t, which is fortunately one of the few ODEs whose solution I never get wrong. That's e to the t. And it starts out at x, so that's e to the t x. So that's the solution. Well, yeah, that's the solution, which happens to be the right-hand side also. So phi t of x is e to the tx, e to the t times x. And then what's the definition of the Lie derivative? The Lie derivative is you take your vector field, you take your form omega, you pull it back using phi star t, and you differentiate that with respect to t and set t equals 0. That's the definition of the Lie derivative of a form with respect to a vector field. Flow the form along, or use the flow to pull back the form and, a distance t, and differentiate that with respect to t equals 0. So this is the Lie derivative of the identity of W. Okay, so we have to figure out what the pullback of this operator is on a differential form. Well, so let's see. So we'd phi t star omega at a point x would take k vectors. And the definition of the pullback was where you evaluate omega at phi t of x, which is e to the tx. And then you multiply each of the vectors by the derivative of this map. This is a linear map, so its derivative is itself. So you get e to the tv1 through e to the tvk. Now, a k form is linear in each of these k things, so I can pull all the e to t's out to the front, and I get e to the kt, omega e to the tx at v1 through vk. But we're also assuming that, that the coefficients are homogeneous polynomials of degree r, so multiplying the argument by this pulls out an e to the t to the power r. So this is equal to e to the kt, e to the rt, omega at x, v1 through vk. Okay, and now I think you can do the rest of it. You differentiate this function with respect to t, you get an r plus k out in front. So this thing here would be r plus k e to the r plus kt omega x of v1 through vk, evaluated at t equals 0. So that's just, and that gives you that this Lie derivative with respect to the identity of omega is r plus k omega. So this side is r plus k omega. We've computed a Lie derivative. And contraction with the identity is kappa, so this side is kappa d omega plus d kappa omega. So that's the homotopy formula. Okay, so I'll stop here, and that's the tool we need, and now we'll get seriously into creating the finite element differential forms in the next lecture.